That's nice.
All right, everybody. Thank you for joining us today for this nice webinar. I'm very excited to have the webinar series from the Traffic Flow Theory Committee, excuse me, back online. It's been a while now, but hopefully it become a steady feature in these crazy times right now. So my first guest is Louis Lehe. As you may know, excuse me again, in 2018 he joined the Civil and Environmental Engineering Department at Illinois Urbana-Champaign. His research focuses on economics and theory of downtown traffic, which is very trendy these days. He received his PhD from Carlos Daganzo at UC Berkeley in 2016. So, my friends, without further ado, the floor is all yours.
Okay, fantastic. So I think that y'all can see my screen in the slideshow. Okay, so let me set my watch. I'm going to talk for, I think, about 40 to 45 minutes, and then we can have some questions about the model. Basically, this is a paper that I wrote with a master's, soon to be PhD student here, Ayush Pandey, who I think is probably on the call. And it's called Hypodemand, a static traffic model with backward bending demand curves. And so we will provide a little context, but first an introduction. See if I can, this little video screen. Okay, an introduction, just introducing myself. I got undergrad in math and economics, and then I went and did transport economics at University of Leeds. Then I went out to Berkeley, where I got my MS in civil, and then I got my PhD in civil at Berkeley. And for the past, I guess, about year and a half, I've been assistant professor at UIUC in the Department of Civil Engineering in the Transportation Systems group. This is me before my hair got long in quarantine. All right, so a little background on this study. The study is basically a novel result. So basically, there's this new phenomenon on city streets, which is pooled ride hailing. So this is not the only way that the central result obtains, the central result being what we'll call hypodemand, but it is basically the inspiration for this study, and the study particularly in the paper, which is submitted to Economics of Transportation. We just got first round reviews, so hopefully it'll get published there. The paper itself uses a model of pooled ride hailing, and by that I mean if you live in a larger city, we don't have it here in Champaign-Urbana, but you have these new pooled options for the big TNCs. So there's UberPool, and then they in turn divide them into like subcategories, such as Express Pool. And then Lyft has Lyft Line, Lyft Shared Rides. In Washington, D.C., and New York, and Chicago, there's a third service called Via that only does pooled rides. But anyway, this is this big phenomenon that's been around since, I believe, about 2016, and has been growing a lot. We'll see how it holds up after the COVID, but in any case. The other motivation for the study is downtown tolling. So there's 5 cities that currently toll downtown areas. There's Singapore, Stockholm, London. Hold on, let me mute that. Singapore, Stockholm, London, Milan, and Gothenburg in Sweden. But it's kind of on the docket in a lot of places. Like New York City actually has this zone here that you see that they anticipate rolling out downtown tolling there at some point in 2021. I don't know if it will be sped up or slowed down by this, but this is the area of Lower Manhattan where they plan on doing downtown tolling. This is a system in Stockholm, and then this here is, at least in a series of plans for San Francisco, this would be tolled. So Jakarta also is considering it. So it's a pretty big deal because there's just so much congestion in these cities, and the initial results from the first 5 cities indicated it really alleviates air pollution a lot. So basically, sort of a background as far as this is a theoretical paper. There's no empirical content in it at all. We don't try to make the parameter values realistic or assume that it would really could be measured in real life. It's more raising the possibility of something theoretical, which is new. So it's best understood. The contribution is easiest to understand by way of contrast with a traditional static traffic model. So this would be a graph of a traditional static traffic model from economics. They're descended from this paper, Walters, I think 1961. So basically you have this PS curve, which is consistent with traffic flow theory right there. And then you have a demand curve, which is basically just says that, this is T is a travel time index, Q is flow on some kind of a road or a facility. And the important thing here is that as the travel time index falls, the amount of driving people want to do rises. So essentially this function TD is downward sloping. And because of that, in the T and this is derived from traffic physics, such as a fundamental diagram or a macroscopic fundamental diagram. If it's a description of a downtown, basically it's going to have a backward bending portion. And so there's sort of a debate in the literature about, there can be multiple equilibria because the demand curve can intersect the supply curve TS in the hypercongested region up here on the top of the curve, but essentially in light congestion, which is this area highlighted in blue, it's only possible to get one equilibrium. So the demand curve is sloping downwards, the supply curve is sloping upwards, so they're only going to meet up to one time in light congestion. But the idea of this study, by contrast, is that, what if the demand curve bended backwards? If it could, QC here is strong as the capacity, but what if this demand curve, essentially what we're going to see is, we're going to make an argument that because of ride pooling, this demand curve can actually bend backwards, and then you could get, depending on how it bends backwards, you could get multiple equilibria in light congestion. So once it bends backwards, you can get lots of light congested equilibria. So that's basically a new source of light congestion of equilibria in cities, and I think it's relevant because in general, in a lot of the MFD studies, we don't see, especially for downtowns, we don't see hypercongestion persist for a lot of the day, or sometimes we don't really see hypercongestion. So this is going to give us the sort of the exotic results that follow from multiple equilibria, even in the somewhat more common case of just light congestion. Light congestion being the traffic flow regime where travel time and flow increase together. I'll say something about how I got inspired to write this study and think about this backward bending demand curve. Well, first it started off with I was programming a simulation for another paper, and one day I got a backward bending demand curve. And so I just thought that it was a coding error, and I kind of just set it down. I just kind of decided, I must have some kind of a coding error. I changed the parameters, and I kind of moved on. But I kept thinking about it. What did cause this backward bending demand curve? Was it really a coding error? And then one day I was visiting New York City, and I needed to take, and it was time for me to go, and I needed to take a lift to the airport. And I was a grad student at the time, or maybe I just recently graduated or something, but I was going to go to the airport, and I wanted to save money because I didn't have any money. So I was like, I'll take an UberPool or a Lyft line or something. And my friend said, don't do that because it's rush hour, so you'll get bogged down forever. So I started to think, okay, so I'm not taking UberPool because it's rush hour and traffic is bad. But by taking regular Uber instead of UberPool, I am in turn causing traffic to be worse than it would be otherwise. because I'm sort of increasing the demand for this driving. Obviously, it's going to hurt traffic more if I take the regular Uber than the Uber pool. So in a way that can lead to multiple equilibria because bad traffic is causing me to take the Uber instead of the Uber pool, and in turn, my choice of taking the Uber instead of the Uber pool is making traffic worse. So there's sort of a circular causation there, which is the hallmark of an equilibrium, and it also means that there could be multiple equilibria. What if everybody took Uber pool, maybe traffic would be light, so the penalty to taking Uber pool would be lower, so that would be like a high pulling, low traffic equilibrium. So then I realized that my model had not been a coding error, it was just that the particular parameters that I had were yielding a backward bending demand curve. So the findings of the study is that, like I said, carpool taxis or pooled ride hailing, they can qualitatively change the nature of downtown traffic. And the basic logic behind this result is that a rise in congestion delays pooled trips more because of detours. So first of all, you have to think about, well, why not take the Uber pool in congested traffic? Why is it like worse to take these options when traffic is bad? There seem to be the whole idea of this is that they must be unusually penalized, and the reason that is that they have to do detours. So I like to think of this as kind of like an edge case. So the cost of that detour, by the detour I mean the way that they work is that they sort of go outside of their way to pick up and drop off other passengers. The time cost of doing so depends on the state of traffic. So if you have to go out of your way by like half a kilometer on some kind of a trip, how much time that actually costs you depends on how bad traffic is. So that means congestion is self-reinforcing. So when congestion is self-reinforcing, multiple equilibria can arise, even in light traffic. So this creates a new role for policy, like a qualitatively different role for policy. First of all, tolls, as we'll see later on, downtown tolls like the ones in Sweden or the UK, can have highly nonlinear effects because they can create and destroy equilibria. And also, under certain assumptions, temporary tolls could permanently reduce traffic. So it's not different than the normal static traffic models in which a toll kind of shifts the supply curve or demand curve up or down a little bit and sort of marginally pushes it to the left or right. And then if you remove it, then the effect goes away. In this model, because we are able to choose among different equilibrium paths, even a temporary toll that moves you onto a better equilibrium could have a permanent impact on traffic. So there's sort of an outline of what we're going to talk about. So first I'm going to set up a simple model of people making choices about downtown travel. I'm going to show how pooled ride hailing begets multiple equilibria, and then I'm going to consider tolls. The general strategy. Okay, so the basic setting is that there's a passengers and a downtown with homogeneous speeds. So by that I mean basically what's called a bathtub or isotropic model or an MFD model. So the downtown has a network fundamental diagram, macroscopic fundamental diagram. So all the vehicles for the whole trip essentially go at the same speed. People choose among three modes for their trips. So they are home, which is a very, very vaguely defined as just not traveling, at least in a way that contributes to congestion. So the model is a bit more expansive than it seems just from the terminology. If I was to get on the subway instead of taking one of the other two modes, then it would count as home. It's just an outside option. Alone, that is a direct low occupancy trip. So that would just be like regular Uber, regular Lyft, or the third mode is pool. So a high occupancy trip that involves detours. So there will be other people in the car with me, but in order to get them, the vehicle is going to have to go out of its way. So this would be like the origin of my trip. This would be the destination. And I essentially am deciding between either just staying at the origin, taking an alone trip, where I go like a direct, let's say the most direct route, like the Manhattan distance, or taking the pooled trip. And the pooled trip is one in which I would, go out of my way a little bit to maybe to get somebody that's right there. And then maybe I have to drop off somebody right there, and then I get back, and then I have to go drop off somebody there, and then I end up at my destination. So the pooled trip takes longer because it goes farther. So the easiest way to think about the sort of the penalty of pool, I think, is to imagine the edge cases. So if travel was at light speed, even though the pool trip takes is a further trip, it has a longer trip. If travel was at light speed, probably almost everybody would take pool because it's cheaper, and the time penalty would be nothing, right? And then if traffic was as traffic approaches zero, the penalty to these extra detours, the time cost of them, approaches infinity as travel speed approaches zero. So that's kind of I like to think of that edge case intuition as light speed and near zero speed. So now I want to talk about the terminology with the trip properties. So T is minutes per kilometer or minutes per distance unit. It's the unit travel time. So it's the inverse of speed. LA and LP are the length of an alone pool trip. So we'll assume that all the trips are essentially the same. And also a very sort of a heroic assumption of the model is that the length of a pool trip does not vary with demand. And that is unrealistic because in real life, as the demand for pooled travel rises, there's matching externalities. If lots of people are taking pool, then the length of a pool trip ought to be expected to shrink because it's easier for Uber to match me with somebody that has almost the same route as me. Again, the edge case, you could think of the edge case of infinite demand. If demand was infinite, there would be 3 people standing next to me on the street going to the exact same destination as me. So there would be no detour. However, since that does not undermine the result, but rather sort of amplifies it, we conduct the model without that dependency on matching economies of scale. So by showing that it's this hypodemand result is able to obtain even without economies of scale, I think it makes it even more credible that it could arise in real life. So then if you just multiply the lengths of the 2 trips by the duration, by the unit travel time, then you arrive at the duration of an alone or pooled trip. So this would be the duration of an alone trip. That would be the duration of a pooled trip. And then you have the occupancy of the trips. So we're going to assume that a alone trip has an occupancy of 1, and a pool trip has an occupancy of phi. So phi could be a realistic number, might be 3. If there's 4 seats in the car, but then some people are getting on and off, it might be around 3. But again, in real life, there would be sort of economies of scale in this. The occupancy would rise as more people take it, but our result, that would just sort of amplify our result. So we ignore it and we just say the occupancy of the pooled trip is fixed. Then finally, we make an assumption about the ratios among these quantities. We're going to say LA is equal to LP over phi, which is another way of saying that the vehicle kilometers traveled is higher with alone than with pool. So basically, this is your sort of your marginal impact on flow from taking a trip by one of the modes. If you take a lone trip, you raise flow by LA. But because the pooled trip is split among some other people, the marginal contribution is LP over phi, because the trip is split among these different people. Okay, very good. So this is sort of the trip properties. So then we'll go into, so this is this is an economic model, so there has to be a demand side. So the demand side is sort of a logit model would be a special case of this. So you could do probit or whatever. So every passenger is characterized by a tuple, epsilon p, epsilon a, where that is their taste for a pool or a loan. It effectively is what kind of benefit they get from they derive from taking a pool trip or a loan trip. Then they trade off that benefit by the time cost of each mode. So there's a universal value of time, alpha. That's just a simplifying assumption. You could do the same thing with a variable value of time. And then you wind up with the utilities, the willingness to pay of the different modes being home. Just staying home, you get a utility of 0. So you don't have a time cost, but you also don't get the benefit of the trip. The utility of pool would be epsilon p minus basically the duration of a pool trip times the value of time. So this is the time. This is effectively the time cost translated into money units, and then this is the benefit of taking your pool trip. And then if you go by a loan, likewise, it's the benefit of taking a loan trip minus the money cost of the duration of the time cost of taking the loan trip. So because LP is bigger than LA, that is to say that a pool trip is just longer than a loan trip, obviously this time cost will be greater for a pool trip than a loan trip. So we have these two. Everybody's characterized. Everybody has kind of a value they would place on one type of trip or the other, so that we can make a distribution over the population of travelers. And that joint distribution is epsilon f of epsilon p epsilon a. And then the total, because the probability density doesn't really have any mass, we multiply the population, we multiply the probability that people choose one mode or the other by this quantity lambda, which gives us the mass of people that choose one mode. So the physics, very simple. So for this present, in the paper, actually we do it in terms of density. And so there's a backward bending portion of TS, but overall, because what's novel is the idea of multiple equilibria, even in light congestion. For the purposes of this talk, we'll just kind of simplify it by saying there's this function TS of Q, which gives the sort of the travel time index flow pairs consistent with traffic physics. So this will just be increasing. You could also, have it be backward bending, but I think that for right now, it makes the most sense just to do the most simple kind of function that you can think of. So now, given that basically now we've set up the model, so we can move ahead to derive the equilibria for the model, and then deriving the equilibria, we see this exotic backward bending demand curve. So basically, the strategy is we're going to derive what we call the mode split among a loan, pool, and home, given a certain unit travel time. Then we're going to derive the flow demanded from the mode split, and then we're going to show how flow demanded changes when the unit travel time rises. That is, that will give us a flow demanded curve. And then from there, we derive our traffic equilibria, the traffic states when physics and demands coincide. So basically, what we can do is we can say what mode do passengers choose? So they're choosing among these three modes: home, auto, and home, alone, and pool. So basically, they're going to choose the one that gives them the highest utility. So we already defined what the utilities were. So if we do a little bit of algebra, just subtracting from both sides and such, we'll see that people are going to choose pool if epsilon p, that is the gross benefit of taking a pool trip, exceeds this quantity that we have on the right-hand side. People are going to choose alone, on the other hand, if it exceeds this quantity. So this is basically saying, by exceeding this, we're saying that the benefit is bigger than the benefit of a loan, and here it's better than staying home. And here, this is true, then it's better than taking pool and better than staying home. So when we draw these conditions, and then otherwise they choose home. When we draw these conditions, we can draw them in an epsilon p, epsilon a space, like here in this figure. we end up dividing sort of the population into these three different groups. So everybody with an epsilon p, epsilon a coordinate, if you will, their tuple, if it lies here in this space, they're going to choose pool. So P for pool. If they have a higher epsilon a, that is, if their gross benefit of a loan is relatively high, they're going to go with the loan, so the regular Uber option. And then if both of epsilon p and epsilon a are small enough, they're going to choose, they're just not going to travel. And this division is particular to a certain travel time index. So this is not exactly an equilibrium, because maybe the choices that they make are not consistent with this travel time index, but if you do have a travel time index, this will give you the demands for each mode. So this is also, I think, an original contribution of the paper, is like thinking of this trimodal choice by plotting it in these in this type of state space. It kind of just makes it easy to reason about who chooses what, and we'll see that in a second when we think of about changes in the travel time index, in the unit travel time. So basically, we're going to derive now the flows demanded. So the first step is the trips demanded. So the trip rate demanded on each mode given some pace or travel time index. So essentially what we do is, to get this, we integrate over regions of epsilon p, epsilon a space. So if I just integrate over the p region, and this line actually goes down, goes out to infinity. There's nothing special happens at 0. But basically, if we just integrate over here, and we would get, the probability that somebody chooses pool, and if we multiply that times the population mass, lambda, that gives us the sort of the number of trips demanded on the rate of trips demanded on pool. Likewise, if we integrate over this region, then we get the rate of trips being demanded on a loan. So essentially what we have then is for given travel time index, how many people are choosing a loan versus pool. And to do that, we just integrate over these regions. That's what these integral bounds give us. And this, again, is the joint distribution of the epsilon p and epsilon a in the population. We go from here. So basically, the flow demanded would be the traffic flow consistent with people's choices given some pace. And essentially what we do is we just take the trips demanded. So we use this notation G here for trips demanded because that's left over from the network exit function theory. They usually use G. But in any case, so you just weight the trips demanded by the vehicle kilometers added per trip. So here we have the pool trip demand, and then we weight it by that LP over phi that we talked about earlier on, the marginal contribution to flow of a pool trip. That gives us this quantity Q, which is the vehicle flows of pool trips demanded given this travel time index T. Likewise, the same thing here. There's no phi because we just said the occupancy of an alone trip is just 1. So this is the demanded vehicle flows of an alone trip given a certain unit travel time. When you add the two together, you get the total vehicle flow demanded, which is what winds up mattering for equilibria. Okay, so now we have this QD of t function. So this is the equivalent, if you recall. We started out with a graph that was like this. So essentially what we've just derived is, so the inverse of this would be maybe a function that we could call TD of Q. It would be this decline, and traditionally this declining function. So here we've done all this derivation. We haven't made any assumptions about QD of T. We just sort of derived it. So we have to inspect, okay, well, which way does this thing twist and turn as you change the travel time index? So what we'll see is that it's perfectly reasonable that it's actually able to go backwards. That is, that QD of T might actually rise as travel time increases or fall as travel time declines, which is in contrast to the traditional model. So now let's do the analysis to see, what are the like, is it possible for this thing to fall is it possible for this demanded traffic flow to rise as the travel time index rises? So let T rise from T0 to T1, just two arbitrary values. And then basically what we do is we just do that mode split diagram that we did in the previous figure. We just do it twice. So this is the original mode split, and then this is the one with T1, which is higher. And so because LP is bigger than LA, basically this point is going to move like that. So it will move, like if you drew a line that had a slope of 1 there, it will move below that line, northeast. So we can then divide this space, just like we did for a given travel time index, we divided the space among pool, alone, and home. Here we're going to divide it in terms of their choices before and after the travel time index rises. So for example, these people, these people really like taking pool. They choose pool before and after. These people choose alone before and after. These people never travel. They just choose home before and after this worsening of congestion that we're looking at. But geometrically, you can see that there exists this region, PA, which consists of people who switch from pool to alone. It just has to exist because of the way that this moves rightward more than this moves upward. And then these consist of people that just quit traveling. They traveled before, but they do not travel anymore. So overall, the number of trips demanded goes down when the travel time index increases, but the point, so some alone and pool passengers stop traveling. However, some pool trips do switch to alone. That's the people in PA. And so basically, if the mass of people that is in this region, PA, is larger than the mass of people in this region, AH, then overall alone trips demanded may actually rise, which is kind of surprising. So if you were running Uber and then you saw that traffic got worse, you would see, there's more people taking the regular Uber now that traffic has gotten worse. Intuitive way to think about that is that example I gave earlier of going to the airport. So because alone, even though overall the number of trips demanded it falls when traffic gets worse, if alone trips, it's possible for alone trips to rise. And if alone trips rise enough, then the flow demanded, QD, can rise. Remember, these are in units of passenger flows, and so that will definitely decline. But because passengers are carried by vehicles and alone trips take more vehicles, then even though the passenger flow is declining, we could see actually more vehicle flow when traffic gets worse, more vehicle flow demanded when traffic gets worse. So what we do is we basically plot the supply curve and a demand curve. So TS is the physical flow pace or flow unit travel time curve. TD is the inverse function of QD. And okay, there's the plot right there. So here we see this is the inverse of that function QD that we just derived. TS is that function that goes like this. And what we can see is actually that because QD can sort of rise as TD rises, that this TD the inverse function can actually bend backwards. So even in light congestion being where TS is rising, get rid of some of my marks there. So even in light congestion, we're getting multiple equilibria. We're getting an equilibria at E2, E1, and E0. So I will kind of go light on the stability analysis for want of time, but we try to have an analysis that shows that E0 and E2 are stable, and this E1 is unstable. And it's a little bit easier to see the stability argument if we plot this instead of in flow unit travel time space, like QT space. If we plot it in density flow space, then it's a little bit easier to see at least to me, why E1 would be unstable according to our argument. So essentially, hey, leave it. If density rises slightly here, if density is out of whack, then the I won't go into it, but you can kind of make these arguments that involve perturbing at each equilibrium. But this is the same plot as the previous one. It's just in a different state space. So we can see here, whereas the hypodemand region before is the region where this demand curve, the green one, bends backwards. Let me erase so you can see it. So what we call hypodemand is the bending backwards of there. Here, the hypodemand is this increase in the flow demanded as density rises. Okay, so finally, we've sort of established the existence of hypodemand. So now we're going to see, all right, well, what is the practical implication of this? And to me, the most practical implication is tolls. There's obviously a lot of different things that follow from a backward bending demand curve, but what I've done here is I consider a toll on vehicle kilometers traveled. So this toll does not yet exist, but it's just functionally it's easiest to insert into the model. So that's the one that I analyze in the paper. Singapore next year, I think, will roll out this sort of GPS-based pricing system. It's called ERP2, Electronic Road Pricing 2. One of the things they've sort of discussed, they have no plans to implement distance tolling. However, the technology that they use could be used for distance tolling if they decide to go down that path in the future. Right now, it's more like if you go into a certain zone or pass a certain point, then you get tolled. But it's not on the basis of kilometers traveled. But in our paper, at least functionally, it is easiest to consider that, so we do. So if we imagine having a toll on vehicle kilometers traveled and implementing it and increasing it progressively, then we can kind of see that, okay, well, the demand curve is going to shift inwards. The green line is the demand curve. It shifts inwards. So for a given travel, in other words, for a given travel time index, there's less flow demanded. And so this causes this is a low pooling, high traffic equilibrium, high congestion equilibrium. This one goes like this. It declines. The E0 equilibrium also declines. It's another stable equilibrium. And then the unstable equilibrium actually increases. So the associated travel time index, which is basically congestion, declines as I increase the toll for stable equilibria, but for the unstable equilibria, traffic actually gets worse as I increase the toll. So basically I regard the unstable equilibria as kind of like more of a mathematical curiosity than anything that's realistic. But if I have this toll tau, then this plot, I've set up a numerical simulation and I just increase tau. If I change tau from 0, if I implement the toll and then I just keep on increasing it for those parameters of my numerical simulation, then I keep track of the travel time index associated with each equilibrium as I increase the toll. What you see is that as they change, E2 and E1 sort of get closer and closer together until a certain point where eventually the demand curve is just going to be perfectly tangent to the supply curve. And for tolls larger than that, they're just not going to intersect up there. So we have this level tau hat here where the sort of the higher congested equilibria simply cease to exist and only the low congestion equilibrium exists. So basically, I have sort of a thought experiment in the paper. So E2, imagine that originally traffic is at an equilibrium where not many people take pool and traffic is really bad. And I start to implement the toll and I increase it gradually over the year or something. And then all of a sudden, if I was the authority, what I would see is I would just see sort of normal traffic behavior where, I increase it a little bit, traffic congestion goes down a little bit, blah, blah, blah. And then I would, I'd keep on doing this. And then all of a sudden, one day when I increased the toll, suddenly traffic would suddenly like drop suddenly there'd be like no congestion and everybody would switch to pool. And maybe it wouldn't happen in one day, but it would be sort of you can imagine there being some sort of like of a path to this point that would involve people every day switching a little bit to pool, and then traffic gets better, so even more people switch to pool, and so on and so forth. So I would be like kind of shocked. I've been increasing the toll for a while and just seeing small results of each toll increase, and all of a sudden I just increased it like infinitesimally. Boom! Now I'm seeing this virtuous cycle where suddenly traffic is settling down at a place with almost half the amount of half the travel time index. The speed is twice as high, and I would likewise see just much higher use of the pooled option. So then I'm like, oh, maybe I just get spooked or something, and then I start to decrease the toll. Well, now let's suppose that traffic kind of tracks along a certain equilibrium that it is at. I'd be like, all right, I'm just kind of spooked, and maybe people are complaining like, why do we have this big toll if traffic is so light? So I get rid of it, so I get rid of the toll, and all of a sudden I discover that even though I don't have a toll, all of a sudden I'm permanently at this equilibrium with high pooling and low congestion because that's under the assumption that traffic kind of tracks along with the same equilibrium. So essentially what I would notice is that a temporary toll, this toll was implemented, increased, and then eliminated, has permanently reduced traffic. So that's kind of an exotic result. And there's no exotic thing about hypercongestion or traffic physics. This is ordinary traffic physics in a light congestion regime like I'm used to seeing, but I am seeing a permanent, this sort of a bifurcation, the bifurcation plot, and a permanent and hysteresis. So that basically ends the analysis. Extensions is obviously the best one is probably economies of scale and matching. That's what my grad student at UCHapandy's been working on. The variable LP, so basically the more demand, the shorter the detours. Variable phi, so the more demand would mean a higher occupancy. But the thing is that neither of these is actually necessary for the result to arise. They just kind of amplify it. And hopefully we'll have another paper soon that will kind of show there's even weirder behavior that happen when these even more multiplicity of equilibria when you count these price changes. Maybe the operators, they are basically increasing prices as traffic gets better. We just have kind of left price out of this. Can hypodemand arise from buses? Obviously, buses are much more common than these pooled services. So can they arise? I have a theory about how that can happen. And then furthermore, having more realistic toll designs, such as ones that don't vary with vehicle kilometers traveled, that might just be like per trip. Or in many cities, such as Chicago and New York, they have taxes on Uber and Lyft, but the taxes have lower taxes for pooled trips. So incorporating something along those lines. Maybe a city, even without taxing all traffic, could switch to a high pooling equilibrium by just not taxing the Uber pool trips, but taxing the Uber trips heavily. They could kind of switch over to another equilibrium. So that's another extension. So anyway, that is my talk, and I'm prepared for questions now. So thank you very much for having me. It's really an honor to do this, and thank you for virtually coming and visiting us here in Champaign-Urbana.
All right, thank you, Luis. That was awesome. Very insightful. Very new results. I have so many questions, but let me give the opportunity to. So if you want to ask a question, please unmute yourselves, or if you want to use the chat box. All right, I think Alex wants to ask something.
How do I? Can't see the chats.
I think they might unmute themselves. Or
yeah.
Well, let me start by asking at the beginning. So the utility at home, you said is 0, right? So that implies. So telecommuting basically would not be part of this analysis, right? Because you can still get some benefit.
It would be. So home is so basically the way to think about it is that the other epsilon, like epsilon P and epsilon A, are just measured relative to home. So it doesn't mean that it's worthless to stay home. It's just that those are kind of like the net benefit of traveling. So if you were telecommuting, it might just mean, and you liked it, it might just
Mm.
mean that your epsilon P and epsilon A would be like negative. You don't even, you like staying at home. Does that make sense?
Okay, 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 okay.
The distribution of epsilon P and epsilon A is perfectly flexible. The results arise no matter how it is.
So it applies to any sort of trips.
Yeah. So basically, anything you can do other
Mm.
than taking the puller alone could be incorporated as the home trip, as long as it doesn't as long as that behavior doesn't impact traffic.
Right, right, okay.
So whether you're taking the subway or you're taking you're telecommuting, it just doesn't matter to us. That's all in home. So I think I'm going to change the name home to outside option to just say
Mm.
it's the thing you would do if you weren't traveling.
Yeah, yeah, that makes sense. All right. Um,
Could I ask a question?
yes,
Sure.
Yeah,
please.
Jorge, one question
Go ahead.
for
Please introduce yourself.
yeah, this is Wen Jin from UC Irvine. Thank you, Luis, for the very interesting presentation and this timely study. And one comment, this, you talk about for reminds me of the most dilemma situation in a sense. If
Yeah.
all people choose, poor would ended up with a better, more social optimal equilibrium. Otherwise, it's a kind of bad one. So that's one comment. And then I have one question regarding, the very, very interesting, the diagram that you, separate the whole domain into three regions.
Yeah.
Um, that is it seems to be a very fundamental result. So I'm wondering. Here it looks like you are using the stochastic utility, random utility theory. I'm wondering how the separation is so clean because using a random utility is kind of just probabilistic. Unless you are using UE model, that then you have I might not have gotten that. So could you please
So
explain a little bit more regarding the diagram? That is very interesting.
So I got the first part about the prisoner's dilemma. So regarding that, basically, yeah, like it could be modeled as so basically like I use a toll to move us from there to there essentially. But if you think about
Yes.
it, if it's not exactly prisoner's dilemma, it's more like the stag hunt game. Uh,
Mhm.
because but so if everybody believed that we were in the stag hunt game, it's hunting stag versus hunting rabbit, then if
Mhm.
we could kind of just I sometimes think if there was like a big advertising campaign where if I believed everybody else was going to take pool, then I would take pool and we would kind of get stuck at that equilibrium. So
Yeah.
if you just think that you could think of it as sort of a game in which everybody moves at the same time, either to alone or to pool. So that is a way to think about it. The second one, I know that you were the audio for me was not great. It was about the distribution of epsilon p and epsilon a. Is that
Yeah.
right?
You have a three regions, one
Three modes.
from three modes. Yeah. So I'm wondering, conceptually, I'm not getting the technical details, but conceptually, if we are using random utility theory, everything is about probability. How can we, divide the space, the domain into three regions? So
You mean like
clearly,
instead of having other modes like 4 or 5 or
yeah,
something?
I make them exclusive. You get what I mean? So it
Yeah.
looks
So
like
basically, so all modes, like I said, the epsilon p and epsilon a are relative to basically h stands in for every mode that doesn't impact traffic, at least your
oh,
choice to
okay.
write on it. So, for example, suppose that there was a bus system. In the
Mm,
bus system, they were not going to change the frequency based on my choice, right? So that would not impact traffic if I ride on the bus. So in that case, taking the bus would count as home. So you're right that it's simplified, but it is a little bit more flexible than it seems. However, if there
mm,
were like multiple pool options, or there's multiple, or let's say that the bus frequency changes in response to demand, then you're right. This two-dimensional plot would be inadequate. I'd have to add more dimensions to it. Like there could be another axis, or it could become like a hypercube. They would become like sort of regions in 4D or 5D space. Then you would no longer be able to represent it in this neat little plot. This plot, two dimensions can only handle three modes, I think. But I'm not up to date on topology, but I think that's how it would work. In any case, so you're right. It would have to be like extended. But overall, I just am kind of showing, that this is possible. And so I think that is a rich avenue of investigation, is showing, adding more modes.
Yeah. May I ask another question regarding, actually the cost structure? You said that, I understand with the pooling, and then, you will take detour. This is the penalty. However, I think there might be a implicit assumption saying that, we always have enough vehicles available, either alone or pooling, so that, the number of vehicles would change. Depending on the rider, the passenger's choice. However, during the rush hour, it is possible that the number of Uber vehicles are in short supply. So in that case, in that case, then the Uber company, this TNC's policy of allocating the resources could have a big impact on whether people the cost for people. I mean, assuming if they allocate more vehicles for pooling rather than alone, service, then, the waiting time to be, assigned a vehicle could be much shorter. So
that's definitely true. So I would think of this as not being so much a super realistic model of dispatching of these services, but rather a simple. The overall issue of hypodemand is that by composition effects, by the change in the composition effects among modes that have different occupancies, you could get backward bending demand curves. So the pooled application is kind of like a special case of that, and it's a simplified one. So if you were to make a realistic model of pooling and such, you would add in a lot more factors. But it's just that nobody's ever derived a backward bending demand curve before, and the point is that it can arise fairly easily. But I agree that if you were to make a very realistic model, there would be a lot of things like they obviously use wait time to ration service. There's a limit on capacity. This is a static model. There's no dynamics to it. So like you said, in the rush hour, the number of vehicles might be low enough that demand is rationed by wait times rather than just travel times. And there's no
Thank you.
Sure. Thank you, Wenlo.
Yeah, thank you very much. Thanks.
Hello, could I ask a question?
Sure.
Yeah, I'm wondering. It seems to me that even if you're at the level where everybody's on carpooling, and you've set the tolls, and you say the toll is, you can take it away. But I think you can't take it away because there'll be people who start moving back to the other end. There'll be people who say, well, I could still go faster without pooling.
Yeah.
And so I think you either have to keep the toll, or you have to have some controller like the law or Uber, who sets a policy that we will not go back to the old way.
Yeah. Well, so the argument that I would make is that people will not go back in sufficient quantity so once we are at the high pooling equilibrium, let me go for it. So basically at this equilibrium, or let's say that it moved, that I decreased it a bit, so we're here, right? So when we're here, people don't really have much of an incentive, or if I was to hear, people actually, as individuals, are satisfied with the way that things are. So they're not tempted to go back because the penalty to taking, they're not tempted to go back because the advantage of going back to alone has shrunk. In the initial equilibrium up here, the advantage to taking a loan was very large, the difference in travel times between the two modes. But at this lower equilibrium, like once we all start to use pool, the disadvantage of pool becomes smaller. So I would argue that people are not exactly tempted in any large numbers to go back to the old one. So I mean, but I think that overall this is very simplified. I think overall that the idea of like just having no toll at all, you might be right that we require some kind of a penalty to really keep traffic down there without accidentally some other factor slipping us back into our old ways. But I guess what would matter the most is simply the fact that there would be this kind of bifurcation level where suddenly we would see the traffics change a great deal because a virtuous cycle would ensue. This virtuous cycle being a situation where as more people take pool, it causes other people to take pool and so on and so forth.
Another question, maybe. I was always wondering how much, in places where you have just two paths you can take, and you have the sign that tells you how many minutes it takes on one, how many minutes it takes on the other. And I was always trying to figure out what would be the time scale for oscillations from people, moving to the wrong place, because it's not a very smart system.
Yeah. So that's a good metaphor because here we don't have like exactly routes. We just have a sort of a generic grid or urban area. So, but you're right that in the sense that in that situation there is a choice that is that there can be oscillations among the choices, like between the two routes and such. And then they have those like simulated annealing algorithms. So I kind of in this paper don't go into particulars of how the choice process happens and how any kind of oscillations would happen. So this is more of just like without being particularly formal about how people switch their choices when I increase the toll. That is something I think that you could study as the oscillations around a choice structure. Because I remember reading a series of papers for a Vickrey bottleneck model by Andre de Palma from the 80s, in which they sort of tried to use some kind of algorithm to see where it settles down, and there was a lot of oscillations there. That would be another thing you could investigate.
Thank you for the questions, everybody. I think we have time for a couple more. So in the meantime,
hello.
Yeah, go ahead.
This is Chen Tian from University of Michigan. Thank you for the very insightful presentation. So I have a question. So in the early stage of your presentation, you presented that as the congestion increases, people will switch from pooling to riding alone, right?
Yeah.
And then under the tolling scenario, is there any regions where actually as you increase the toll, because the pooling choices have so much detour, so the equilibrium will actually goes like in the opposite direction, where people instead of switching to pooling choices, they will switch to riding alone and then make the system worse off.
Yeah, for brevity, so I have a plot like this in the, so you're talking about this, I'm sorry, I've covered it all up with marking, but you're talking about this one. And I think that what you're asking is like, if I did this for the toll, so this is showing a change in travel time. So it's showing a change in travel time. So you're saying like, if I did this for a change in toll, could I likewise, is there anything hard I could say about the direction of switching? And the answer is that in the paper, I didn't go into it, but essentially because I consider a vehicle kilometer travel tax, and we also assumed that the vehicle kilometers that you travel by alone are greater than pool. So when I increased the vehicle kilometer travel tax, the cost of a loan rises more quickly than the cost of pool. So that means that people take less. Basically people overall people travel less, but people switch to only switch from a loan to pool. No one switches from pool to a loan because the cost of a loan is rising faster with that toll than the cost of pool. Because I said it was a vehicle kilometer travel tax. And I'm kind of vague about how that tax is implemented. Like in a world where, like this world where all the trips are like of uniform length, it could be charged to the passenger. But I sort of say that in real life, what you do is you just charge the vehicles as they drive around, and that would kind of be passed on to the passengers. But in any case, so yes, in the paper I have a diagram like this, but it's for the toll increase, and it can be shown that people only switch from a loan to pool as the toll rises. Very good question.
Got it. Thank you.
Hey, Luis, there's a question in the chat by Eddie Wilson.
Okay.
Let me read it. It seems to me the pitchfork bifurcation that you discuss here could arise in other ways, but for example, by a public transport system whose performance benefits from economies of scale. If you could comment.
Yes. So in the conclusion of the paper, I discussed the fact that what we're considering here is a very special case of hypodemand. But hypodemand can arise. The basic mechanism of what I call hypodemand, the backward bending demand curve, is that whenever people face a choice between a high occupancy mode and a low occupancy mode, first of all, and second of all, whenever a rise in travel time, whenever a rise in congestion hurts the high occupancy mode more than the low occupancy mode. So it's about relative penalties. Any model, like a model of bus service, or a model of bus service in which congestion hurts bus more than car, would also give you hypodemand. And then the way that it might hurt bus, it could hurt it by simple traffic physics. Maybe it causes more bunching. Or you could also hurt it by, like you said, depleting economies of scale. But overall, like hypodemand is generic, and I would hope that like these are the very obvious extensions, is deriving hypodemand in a lot of different ways and starting to think about our cities as, instead of just saying, oh, the purpose of policy is slightly shifting these curves, like we're going to slightly increase capacity, we're going to slightly increase like transit ridership by lowering the fare or raising the frequency. Instead, by the recognition of hypodemand, we see that the role of policy is really affecting these bifurcations and choosing among equilibria that are stable once obtained. So for buses in particular, what I think of is that even if I don't have any special theory about bunching or anything, if the penalty of time spent, if people dislike spending time on bus more than they dislike spending time on car, even if both of them have their travel times change at the same rate, like that would be if the buses go at the same speed as cars, then also have stop times. If people dislike spinning, that'd be a bigger alpha for bus than for car in my model. Then a fall in congestion would actually lower the sort of the utility cost of riding the bus more than the utility cost of riding the car, and we could see hypodemand simply from a bus model.
All right, so it's a much more general model than just for UberPool, right?
Yeah, and in the paper, I kind of draw that out a bit more. What I'm doing here is really raising the possibility of like all you need to get this hypodemand is just like my model is of UberPool because that's what inspired it, and I think it's interesting to think about. But at the end of the day, it's just the fact of you're choosing between a low occupancy, high occupancy mode, and congestion hurts the high occupancy mode worse than the low occupancy mode.
Mm-hmm.
What does that mean for transportation management?
I can help but ask you, what would happen if you consider the back-bending supply curve?
Yeah, that's a good question. So in my paper, I didn't, because the backward bending, I didn't. So you could get a bunch of equilibria.
Yeah.
And some of them could be very weird. Like you could have you might have the demand curve going that way, and then the supply curve going that way. So I didn't get into that mainly because I'd read a lot about the stability analysis of these hypercongested equilibria, and it's obviously it gets very complicated even with just like a demand curve going in one direction. So I'm not an expert in this type of dynamical systems and stability analysis and such, so I kind of have left that for further. But you could get like a bunch of equilibria, and they could have very complex stability analysis. Because not all the equilibria are sort of worth even thinking about if they're not really could not possibly obtain.
But the results you presented apply only to free flow? Is that fair to say?
The plots are only shown for free flow, and the stability analysis was only done for like free flow. But I think that you could do it. I just haven't done it for hypercongested equilibria.
I see. Very good. Maybe one more question.
Sure.
All right. So I guess that's we can leave it here then. Again, Louis, thanks so much for opening up this new series of webinars. And if we could clap electronically, that'd be great. But thank you so much again. And to everybody, thank you for coming. I'm glad to see that so many people showed up. And let me announce our next speaker is going to be Wenlong Jing in exactly 1 week from today. So next Thursday, same time. He's going to talk about some very interesting developments on MFD theory. So he found a way to unify all the existing models, and I think that's going to be very interesting for next Thursday. So again, Louis, thanks so much, and thank you everybody for coming today, and we'll see you next week.
All right, thank you for coming out, everybody. It's really an honor and a pleasure. Thank you.
And I'll be posting the link shortly, okay, to the recorded video.